So now we're going to look at a hypothesis test that will examine the population linear correlation coefficient. And we learned in chapter 14 that R represented the correlation coefficient. Remember that? And if you recall, R went from -1 to 1. And anything between -1 up to 0, anything that was negative was negatively, showed that the two variables were negatively correlated. Between 0 and 1 showed that they were positively correlated. 0 meant no correlation, and the closer the value was to -1 or to +1, the stronger the correlation is. But when we talk about correlation of a population, we have to introduce a new variable called rho. That is not a p. That is the Greek letter rho. It kind of looks like a fancy p. You can look at your formula sheet and you will see it right there. So definitely, it looks a lot like a p, but it's not quite a p. Oops, sorry, wrong one. So that variable is our population correlation coefficient. And very much like the sample one, if rho equals 0, there is no correlation. Our two variables are uncorrelated with each other. Now, if rho is greater than 0, we say that our variables are positively linearly correlated. And the same sense, sorry, if rho is less than 0, we say our variables are negatively linearly correlated. And if rho does not equal 0, we just say the variables are correlated. Or linearly correlated, sorry. Linearly correlated. So basically, when you are determining your alternative and your null hypothesis, this here is always going to be, your H sub 0. Your H sub A will be one of these, and it will depend on what's written in the script. Kind of like when we did mean hypothesis test for means. If it said less than, it was a left tail test. If it said greater than, more than, we did a right tail test. If it simply said they're not equal, we did a two tail test. So in this case, if you see the word positively linearly correlated, you're going to use greater than 0. If you see the word negatively linearly correlated, you're going to use less than 0 for your alternative. And if you don't see either of those words, you just see linearly correlated with no negative or positive, meaning no direction to go in, you're just going to simply write not equal to. So let's take a look at an example, and we're going to use the data, again, that we've been using for all of our examples. And let me write the question that will correspond to this. So let's say at the 5% significance level, do the data provide sufficient evidence to conclude that the hours you study, the hours studied, and test grade are negatively correlated? Now, the reason I can ask if it's negatively correlated is I actually have a negative correlation coefficient. You would not see something, say, negatively correlated with a positive correlation coefficient. And the opposite is true. You would not see a question that's asking you to check if it's positively linearly correlated with a negative correlation coefficient. So they have to coincide, and they will. If it doesn't have the word negative or positive, then your sample correlation coefficient could be either or. Okay. So let's first just do our hypotheses, of course. H sub O, as I stated, you can even look at your formula sheet. It's always simply going to be rho equals 0. Now, for H sub A, you have to read, I am asking for a negative correlation. So because of that, we can state rho is less than 0. Okay? To get our information that we need, which is step 2, we first need to know our test statistic formula so we know what information we need. Go to your formula sheet. Here's your test statistic formula. It's R, which is the sample correlation coefficient, divided by the square root of 1 minus R squared over n minus 2. So let me write that down. It is a t-test statistic again. The entire thing is under a formula. So here's the good news. We only need one value. So back in one of the videos from chapter 14, we already found the correlation coefficient for this particular problem, and we found it to be negative 0.77. You can go back and look at those videos to see that. We have a significance level of 0.05. That's the only information we need to do a t-test to get our test statistics. So we're going to go ahead and plug that in. Be careful with the minus sign. Okay. Yes, when you square the negative 0.77, it does become positive. But you still have 1 minus point. So negative 77 squared is 0.5929, but it's still 1 minus that because there's another negative there. Of course, over 6. So we have negative 0.77 over. So I got 0.4071 divided by 6, 0.06785. Take the square root of that. And I am getting negative 0.77 divided by 26048. And I got a test statistic of about negative 2.96. Okay. So for step 4, you can do your p-value or your critical value approach, whichever one you want to do. I did a critical value in the last problem, so let's go ahead and do a p-value approach. To do a p-value approach for this particular problem, this is a left-tailed test. All right, you can tell from your alternative hypothesis. You're going to go ahead and put your test statistic in this location, because again, we're going to do a p-value approach. We're going to try to estimate what this p-value is. One of the things you should check up here in number 2, of course, because we are running a t-test, we do need degrees of freedom, which is n minus 2. So that is 6 degrees of freedom. So go to your t-chart, look up 6 degrees of freedom, and see where 2.96 would fall on that chart. And for me, I am finding that it falls between 2.447 and 3.143, which makes it between the areas 0.01 and 0.025. That is where my p-value is going to fall. It is one-tailed. We do not need to double that. If that's where my p-value falls and I know my alpha level is 0.05, I can see that p is clearly going to be less than 0.05. Since p is less than 0.05, we can reject the null hypothesis. And we can state that at the 5% significance level, the data do provide sufficient evidence to conclude that the hours studied is negatively correlated to your test grade. Now, if we were in class, I would have a little discussion about, okay, why is that? It kind of seems the opposite should be true. The more you study, the higher grade you would get. But there's a lot of different reasons why this would happen. The student who's studying more could just be weaker and who doesn't grasp the concepts. So they're studying more, but they're not studying effectively, which means they're getting a lower grade. The student who is getting the concepts easily doesn't need to study, so they're getting higher. There's a lot of different reasons, but we would certainly talk about that. Okay, thank you.